Hello and welcome to our virtual Lunch and Learn. Today we're talking about wireless network with Prosoft Technology and Industrial Wireless. My name is Rachel Green and I'm the Digital Communications Specialist here at McNaughton-McKay Electric Company. Presenting for us today will be Jeff Thacker, Automation Consultant operating out of our New Bern, North Carolina location. And out in the comments section, ready to answer your questions today, is Victor Perangelo, Regional Manager with Prosoft. We'll also have a Q&A portion at the end for Jeff to answer your questions in more depth. We'll be getting started shortly, but we'd like to allow a few minutes for attendees to join us. As you come in, let us know where you're tuning in from in the chat window. As we continue to socially distance, we're happy to be able to host these live sessions on YouTube, making it possible for you to be able to join us from the comfort and safety of your own homes and offices. You can view recordings of previous virtual Lunch and Learns on our YouTube channel under the Virtual Lunch and Learn playlist. And we will be continuing this series every Wednesday at noon, so be sure to join us on your lunch break. For anyone just joining us, welcome to our virtual Lunch and Learn Wireless and Networking with Prosoft Technology, Industrial Wireless. Let us know where you're tuning in from in the comments. We'll be looking for questions as you have them in the comments while our presenter, Jeff Thacker, discusses the basics of wireless communications, including the benefits of using wireless networking, typical wireless applications, site surveys, design and deployment considerations. Prosoft Regional Manager Victor Perangelo will be available to respond to your questions in the chat as we go along. And we'll also have a Q&A segment at the end of Jeff's presentation to address some of those questions in more depth and to allow some time for any follow-up questions you might have. If you'd like to reach out afterward, or if you have further questions for Jeff, you can send us an email at macandmaclive@macandmac.com. Be sure to let us know which session you attended and we'll direct your questions to Jeff. We'll have that email address on the screen for you at the end as well. All right, it looks like we have a number of attendees now, so let's go ahead and get started. Jeff, I will pass it over to you.
Thanks, Randy. I want to thank everybody for taking the time to join us today. So let's get started. So here's our agenda. We'll start with a brief introduction of Prosoft, who they are and some of their experience in the industrial market. We'll then move into a discussion of industrial wireless. It'll start pretty basic, and then we'll get into more detail as we move along. But most of the presentation today is just going to be a discussion of the key things we need to consider when we're developing a wireless network. So who is Prosoft? Most of you may already be familiar with Prosoft. They've been a valued Rockwell Automation and Compass partner for many years. About 30 years ago, when Prosoft was first started, their core business was primarily a portfolio of protocol converters, and this is what Prosoft was originally best noted for. And then about 15 years ago, around 2004, Prosoft started its IEEE 802.11 industrial wireless business. And now more recently, Prosoft is offering cloud connectivity products that allow the customers to connect to their applications from anywhere in the world. So this slide shows how Prosoft is structured globally. In addition to marketing and sales, they provide application support around the clock, 24/7 technical support. And it's important to note here that all the Prosoft regional managers themselves are application engineers with years of experience in industrial wireless applications. This slide shows a little bit of services that Prosoft can provide, development of specifications, which is detailing the overall requirements of a wireless system. They can provide system design, supporting the hardware selection and configuration of the radios. They can do site surveys, which is coming on site to do an actual live test of equipment that's been proposed. They'll help installation, supporting, and provide guidance and recommendations to support your installation. And then, possibly most important, they'll do a post-installation survey or validation, which is a final test of your newly commissioned system. So let's get started. we'll start with a simple question. What is industrial wireless? It's governed by IEEE 802.11, we just mentioned, which is a set of standards that define the communications for wireless networks in general. So what this means is fundamentally it's the same technology as the Wi-Fi that you use in your homes and your offices. So it's important to note here that if you can set up your own home wireless network, then you can definitely do the same for an industrial application. So the next few slides will talk about the IEEE 802.11 standard and how it's evolved. Back in 1999, the 802.11 started with the B amendment, and the B amendment provided data rates at 11 megabits per second. However, it was quickly realized that 11 megabits just would not be fast enough. So in parallel development, Amendment A was developed, and Amendment A gave us speeds of 54 megabits per second. And it's this higher 54 megabit speed that really established the usability of 802.11 for industrial wireless. You also may note here that in the B amendment, it operates on the 2.4 gig band, while the A amendment operates in the 5 gigahertz band. And then later in 2003, the G amendment was added, and this gave us speeds all the way up to 54 megabits per second, but it was limited to the 2.4 gig band. And then in 2009, the N amendment was introduced, which gave us speeds all the way up to 300 megabits per second. And it also provided functionality in both the 2.4 and the 5 gigahertz band. It also added a couple new technologies, which is channel bonding and MIMO antennas. We'll talk about that a little bit later. It's also important to mention the AC amendment, which gave us speeds up to 1 gig. AC is popular in commercial applications with things like office Wi-Fi and such, but not so much in industrial wireless. And then finally, we come to the AX amendment. AX is not scheduled to be ratified until later this year. And with the AX, estimated maximum data rates of 11 gigabit will be possible. This slide shows the life cycle of the 802.11 amendments we just mentioned. On the left side of the curve is the newer technology, and then on the right side of the curve is the older technology that's ending or nearing its end of life. You can see here that there's still not many applications using the B technology, which was that slower, 11 megabit in the 2.4 band. There's still some using G and A, and it's clear that the N amendment is the most popular. AC is starting to become more widely used, and the AX that we just mentioned is just getting started. So as we just mentioned on the previous slide, 802.11n is the most widely used. It provides faster data rates in both the 2.4 and the 5 gigahertz bands. It facilitates the use of MIMO antennas and channel bonding. MIMO stands for multiple input, multiple output. It's a technology that uses multiple antennas at the transmitter and the receiver to provide multiple data paths to carry data and increase the overall communication capacity of the link. Channel bonding occurs when two adjacent 20 megahertz channels inside a specific frequency are joined to create one larger 40 megahertz channel. So you effectively double the throughput of the communications between the wireless radios. So what are some of the very basics? Although, as we know, a radio is a gadget that we listen to, it also means something else. The word radio, if you look it up, means sending energy with waves. In other words, it's a method of transmitting, electrical energy from one place to another without any kind of direct or, wired connection. Transmitting radio basically pushes alternating electrical current through a cable into an antenna, which makes electrons vibrate within the antenna, which in turn causes radio waves. And then the radio waves are then sent by the transmitting radio through the air at the speed of light to the receiver. The strength of a radio signal, or the RF power, is measured in dBm. And dBm represents decibels referenced to 1 milliwatt. And the key indicator for signal strength at the receiver is referred to as RSSI, which stands for Received Signal Strength Indicator. The RSSI is also measured in dBm, but it's important to note here that it's measured with negative numbers. So the closer to 0, the better. For example, an RSSI of -50 is better than an RSSI of -70. And when designing a wireless network, Prosoft recommends designing a system with an RSSI of around -65 dBm. If you look at the specifications of a radio, you'll see that -65 dBm is far below the rated sensitivity of a Prosoft radio. So why would you use or design for such a low RSSI? Well, by using this lower number, you're actually using it as a design criteria or as a baseline to give you a cushion to withstand signal losses due to things like environmental interferences. And this cushion or this baseline is actually called fade margin. So when you hear about radio communications and fade margin, what you're talking about is actually a design allowance that you design to that expects and accounts for signal strength degradation. And that degradation can happen from such random factors as weather or growth of trees or anything that might cause a reduction in signal strength over time or due to a weather event. So how is a wireless network different from a wired network? For a wired network, depending on your environment, you might use standard office grade cabling or 600-volt rated cabling or even armored cabling. And within the cable itself is a shield that protects the communications from electrical noise. But where it's different in wireless is that in wireless there is no environmental shielding. So the transmission of the radio waves from one antenna to another that we call RF propagation can be affected by different types of interference. So in a wireless system, there are two major types of interference. You have attenuation and multipath interferences. Multipath reflections can happen when radio waves encounter different obstructions like trees or buildings or whatever, and this causes the radio waves to arrive at a receiver at slightly different times or at slightly different angles, and this can cause signal distortion. So when that happens, retries obviously are going to occur. Now with attenuation, attenuation basically is when a radio wave passes through one medium to another. So everything has attenuation. Like the human body can attenuate a signal by as much as 3 dB. Drywall can attenuate a signal by as much as 4 dB. If you're passing signals through a concrete wall, the concrete wall can attenuate a signal as much as 10 dB. So you have to do things to maintain signal strength, and one of the things you can do is choosing the correct antennas with the correct dB gain, provide direct line of sight with as few obstructions as possible, using low loss cables. Anything you need to do to try to overcome any of those things that can attenuate your signal. I just mentioned choosing the appropriate antenna to ensure signal quality or signal strength. So this screen shows an example of the radiated energy of an omni antenna and for a directional antenna. So for an omni antenna, you can see that it radiates and receives energy somewhat equally in all directions, whereas the directional antenna has the ability to focus its energy in a particular direction. So in many applications, what you'll find is you'll have an omni antenna that's used as a centralized hub, and that it'll communicate to multiple sites, multiple remote sites, and then the equipment at those sites will use directional antennas communicating back to the omni master. So the radiated energy of an antenna is going to be shown in spec sheets as a graphical representation that, kind of like we show here on the right. It represents the relative intensity of the energy that's going to be radiated from the antenna in a particular direction. So the gain of an antenna is merely a performance number. It's going to pertain to the antenna's ability to effectively direct radio waves either in a broad fashion like an omni or in a more narrow directed fashion like a directional antenna. And it's important to note here that antennas do not create energy. when you talk about an antenna with a certain amount of dB gain or whatever gain, it's not creating energy. Then the antenna is merely direct or concentrate energy, kind of like a mirror diverts light or like a magnifying glass might focus light. So before wrapping up our overview of the basics, we need to talk about frequency channels. The overall wireless spectrum is regulated, and we're not free to use any frequency that we want. But the good thing about 802.11 is that it operates on an unlicensed spectrum that doesn't require any FCC approvals. So here on the left, we show the 2.4 gigabyte spectrum, or excuse me, 2.4 gigahertz spectrum. This was the first spectrum that the FCC made available for unlicensed use. But as we mentioned earlier, it became very popular and very busy. So on the image on the left, you can see that there are 11 channels in the 2.4 gigahertz band. And if you look even closer, you can see that there's 3 channels that do not overlap or do not interfere with each other. And we're showing those here with the in red. And these channels are channels 1, 6, and 11. So these are typically the preferred channels that you'll use in the 2.4 gigahertz band. On the other hand, if you look on the right, at the 5 gig spectrum, you'll see that there are 9 non-overlapping channels. So combined, this means that you could have as much as 12 independent wireless networks operating in close proximity without any competing channel interference. So a good analogy for selecting a channel is kind of like selecting a lane on a highway. It's better to pick a lane with the fewest amount of traffic on it. So the remaining of this discussion is we'll basically be talking about some of the things we need to consider when we're designing a network. So here are a few things that can have a negative impact, and we'll cover these in the next few slides. First of all, network interference is the main cause of packet loss. The interference that exists will degrade signal quality, and it will cause the radios to receive incomplete data packets. So interference can be reduced in a couple of ways. You can improve the signal strength quality by using higher gain antennas. You can use lower loss antenna cabling. That's going to give you lesser of a loss over your antenna cable length. Use the shortest possible cable that you can. Or, like we mentioned before on the highway, you can choose an unused frequency channel or maybe an underutilized frequency channel. Next, we have latency, which is basically the processing time of sending and receiving data. So if a wireless network is exposed to interference, data packets can be received by the radio and be received with errors. So this will cause the receiving radio to send a message back to the transmitting radio to resend the data. And this duplication and resending of data causes additional time, and this additional time is called latency. Next, when designing a system, you need to know your throughput requirements and your bandwidth requirements, and this will allow you to design your system accordingly. Knowing these things give you a baseline for assessing your network performance later after your system is fully installed and commissioned. So throughput tells you how much data is being transferred from a source at any given time. Bandwidth tells you how much data could theoretically be transferred from a source at any given time. 50 megabits is typical in a wireless system, but as we mentioned before, with 802.11n, data rates up to 300 meg can be achieved. If you have a mobile system, a wireless connection may automatically switch from a connection with a weaker signal to a connection with a stronger signal. And this is referred to as wireless roaming. So when a device switches, the network and the data connections are briefly interrupted. So a huge benefit of Prosoft radios is that they can provide near seamless roaming with a switch time of about 10 milliseconds or less. When we talk about range, the higher the frequency of the signal, the shorter its range. So this means that a 2.4 gigahertz signal can communicate over a farther distance than a 5 gigahertz signal. Also, a 2.4 gig signal can penetrate solid objects better than a 5 gig signal. So an important note here is that although strong signals in long range may benefit your network, it could still cause interference problems with other existing networks. So how easy is it to put a system together? Well, in a simple case, you can put a standard point-to-point system together in your office on your desk, say easily in about 30 minutes. You basically take out the radios, plug in the antennas, connect up some DC power, power them up and do the configuration, you're done. But before getting ahead of ourselves, there are a few things we still need to consider before starting our design. When you're buying a home or office grade system, possibly price and speed are the only things you consider. But with an industrial wireless system, there's quite a few things more. To help, Prosoft actually provides an application questionnaire. It's something they offer. It includes questions like, what type of application do you have? Is it a station application or is it a mobile application? If it's a mobile application, does it require power communications throughout the entire travel or only in certain areas? What are the typical environmental factors at the location of the radio, where the radio is going to be installed? What's the environment where the antenna is going to be installed? If it's outdoor, what are the extreme environmental factors such as rain, snow, high winds, or hurricanes like we just had? How many sites do you have, and what's the distances between those sites? Are we talking about a matter of feet or miles, and also, do you have clear line of sight between your sites? What type of data are you going to be sending? Is it an Ethernet IP packet, or is it a Modbus TCP/IP packet? You need to know your throughput and your bandwidth requirements. When we talk about Ethernet IP and Modbus TCP packets, you need to know how much data is inside that packet. And we're not talking about these things just because we're considering an application is just point-to-point between two radios, but we need to know these things for all radios across the entire site, because the system has to have enough bandwidth to handle all communications between all the radios that might try to communicate at the same time. So here are a few things you need to consider beforehand to help you design a wireless system, a reliable wireless system. You need to make sure you have good line of sight between your radios. You need to make sure that you have an RSSI or receive signal strength of around -65 dBm. You want to use directional antennas where you can, and you need to use antennas and cables to give you minimal losses without excessive gain. And that's actually pretty important. Using the highest gain antenna and having the highest gain signal does not necessarily ensure the highest received signal strength. If an antenna gain is too high, it could actually focus the RF energy so strongly and so narrowly that it could shoot right over the receiving antenna and result in no signal at all. Another thing you should do is you should always install the radio at a location that will allow you to use the shortest possible cable to your antenna. A shorter antenna cable is going to induce less signal loss than a longer cable, obviously. And there's also different types of cables. Some have an inherently less signal loss per foot than others, obviously at a higher cost. But and also, like I mentioned before, you want to make sure that you operate in an unused channel or a channel that is free of existing traffic. Another thing is to, if you are communicating with a Logix controller, you want to make sure that your RPI is set correctly. You do not want the RPI to be set too fast. For a wireless system, the RPI is going to be set a little bit higher than a wired system. Another thing is you also want to use, where you can, unicast messaging, and at all costs try to avoid using broadcast. This is going to minimize the data and the traffic that's on your network. So to rehash what we just said on the previous slide, these are your keys to success for a robust network. Always attempt line of sight between your antennas, select appropriate hardware for sufficient signal strengths, you select unused or unutilized communications channels, and then manage your wireless traffic using the appropriate radio configurations. So this brings us to the wireless survey. So before installing a system, you really should conduct a wireless survey. A wireless survey is a live on-site test to verify your preliminary design assumptions. So everything you've done up to now, you want to actually test it to make sure everything's working properly before you actually do the installation. So during the site survey, measurements are taken, data is gathered, and then the information is analyzed to ensure that your preliminary theoretical design actually lines up with the actual performance you're receiving. So with the site survey, what happens is a Prosoft engineer will come on site and he'll bring all the equipment that was specified for the application. They'll bring it to the site. It'll be temporarily installed. It'll be powered up, and then they'll move around the actual path where the radio is going to be installed and where they're going to be communicating. And they'll look to see if the RF power is what they expected. Is the signal strength within tolerances? Is the signal strength too weak or is it too strong? If the signal is weak, are there obstructions or any other source of RF noise? They'll be looking to see if there's any existing channels of RF traffic in the area. They'll look to see if any of those channels are open or free or contain minimal traffic or too much traffic. So again, the site survey is merely done to ensure that your preliminary theoretical design is going to provide the performance that's expected of the application. So you just completed your survey. You know what hardware you need. Everything's been tested out. You've ordered the hardware. You've received the hardware. Now it's time to install and commission. So after everything's installed and wired up, then what? The Prosoft radios are configured using an internal web page. You just use a standard browser like Chrome or Firefox. You can configure the radios in the field after they've been installed, or more commonly, most people configure the radios beforehand in their office and then just install them afterwards. The radios can be configured to communicate directly to a Logix PLC. Prosoft has an add-on instruction to help you with that. This allows the PLC to actually know that the radio is powered up and that it's on, that it's operational, that it's healthy, that your signal strength is good. It'll even allow you to know exactly what the signal strength is. And then all this information can be pulled back from the radios to the PLC and then ultimately displayed on an HMI for diagnostic purposes. So like I just mentioned, to configure a radio, you just use your web browser, and all these configuration parameters are set through that internal web page. The page also allows you to save the configuration to your computer. So this will allow you to quickly commission other radios by creating a template file that you can upload to other radios as you're doing your commissioning. So after the system's actually installed, everything's up and running, next comes possibly the most important and probably the most overlooked step, which is validating the system. When Prosoft validates the system, the engineer comes back on site and then they continue their testing. They make sure that all the radios are indeed set up properly. The master radio is set up properly. The repeater radios, the remote and the client radios, are they set up properly? They check to make sure that the necessary security settings are applied. They check to make sure that the data is flowing properly between the radios. They also check to make sure that they can push and pull data through the radios and that the bandwidth is truly accurate and can provide what the requirements are. So in general, again, validating a system is a very important step, and it basically ensures that your newly installed system is truly operating as was originally designed. So why would we even want to use wireless? So Wireless Ethernet is actually the #1 medium of network access in the world. It can be used anywhere that a physical Ethernet cable can be used. So anywhere you have an Ethernet cable, you can use 802.11 wireless. Often the case, it's actually preferred due to the higher cost of running cables, or due to the distance, or just basically because of the lack of accessibility of where you need to install your equipment. In some applications, it's the only way to attach to equipment. For example, if you have a mobile application like a crane or an automated guided vehicle, wireless is the only way to go. Again, wireless is becoming more and more popular. It's actually growing about 20% faster than the physical wired connections. So industrial wireless can be used in a lot of different industries. It provides the potential for faster deployment for your projects, because you'll have connectivity without having to pull all those cables or possibly all those long runs and all those trenches. You'll have increased uptime because you can pull back all this diagnostic information from the radios that you didn't have access to before. It enables smart manufacturing, so you can connect to autonomous machines that move freely throughout the floor based on it being a mobile application. And so regardless of the industry or your application, wireless does have some definite advantages over a wireless network. So what are some examples of how wireless can be used? So here's a typical application. You've got your enterprise network, a business network that's pulling data from the factory floor or from a controller. Then you got the controller where your PLC is pulling data from your control network or your device level network. And this is the type of application we'll be talking about today. Those applications that are on the factory floor where timing is most critical. So let's say you have a control network that might consist of control objects PLC, some static switches that are eventually connected all the way back to your network core. It also could be connected remotely to a control cabinet over wireless, kind of like what we're showing here. Or that remote equipment might be an automatic guided vehicle. And in this example, the AGV may have a compact Logix on it or a micrologix or some other type of IO. And since the AGV is obviously mobile, it has to communicate back to the main controller using some sort of wireless method. So what are some other applications? We can split wireless applications into two basic categories: stationary applications and mobile applications. Stationary applications are everywhere, kind of like oil and gas or water and wastewater. In stationary applications, you're basically connecting to outlying equipment that might be over a large area, or a large city. It's also used in infrastructure, for the same purposes. Using wireless for industrial mobile applications is growing more and more. Industrial wireless can be used for control of AGVs, cranes, or any other untethered type mobile application, like one that might require collision avoidance, for example. On this slide, we show a stationary application. You can see on the left, we've got a master access point that's connected to a main control panel. And this master is connected to several other radios in repeater or bridge mode. So from these access points, we can connect even further to other remote equipment like we're showing here on the right. Excuse me. When we talk about mobile applications, we're talking about an application where the automated equipment is moving throughout a facility. So in this type of application, there'll be a radio or a mobile cart or a mobile machine that communicates back to several fixed access points throughout a factory. And while the mobile machine is moving from place to place, it may become too far from one given access point. So it has to quickly establish communications or roam to another access point in order to maintain connectivity. So as it's moving throughout the factory floor, you got to remember that wireless Ethernet only has a certain amount of range or area that it's going to cover. So as this mobile carrier is moving along a production line, it may be hopping from one antenna to another or from one radio to another. So what we're seeing on this slide is that the mobile carrier may initially have been connected to the master in the control room, but then after a certain distance along the line, it may be connected to a different access point. And then as it moves along the line, it could connect to another and another. So the key thing here to note is the radios need to be able to roam and switch at a fast enough rate so that the PLC does not, drop communications. And like I've mentioned, I'm sure several times before, Prosoft can switch and roam in 10 milliseconds or less. Just as important, talking about roaming, the Prosoft radios can roam and switch without the need of a LAN controller. So some systems out there require wireless LAN controllers that'll coordinate the traffic and the roaming handoff. But Prosoft does not require that. They all have the algorithms inherent within their own radios to handle that. So if you look in the upper right-hand corner, you're going to see a statement on the slide that says no set of sequence access points is required. This means that the Prosoft radios already have the algorithms built into them that will allow them to see a signal of a better connection or a stronger signal and make that switch to that new connection automatically. So in a mobile system or conveyance system, as we see here, you might have a hardwired Ethernet backbone that has an array of access points providing coverage along the production line. And then you might have 50 or 100 more carriers or whatever moving along that line with their own radios communicating back to the master or back to a main server. Another way of implementing a system like this is instead of using multiple access points, but using a long, what's called a radiating cable, and using that in place of a hardwired backbone. You can think of a radiating cable as a long linear antenna that can be installed along the full length of a production line. So this slide shows a section of a radiating cable. It's basically a long antenna that can be installed along the full length of a production line. So this picture shows a few different conductors. You got the inner conductor, you got the insulation, you got the outer jacket. But the basic principle is that it propagates RF out of slots that are cut in the outer jacket. And these slots are specific to the desired frequency of the network. So a 2.4 gig slot is going to have a different size than a 5 gig slot. So if you look at the picture again, and if you look where the RF is coming out of the slots, you'll see that the antenna aboard this mobile carrier is looking at the RF exactly where it's coming out of those slots. So as the mobile carrier moves along the radiate cable, it will move at a fixed distance so that no matter what the carrier is doing, whether it's going up or down or around curves, that mobile carrier is always going to be a fixed distance away from the radiated cable, so it'll always be well positioned to look directly into those slots. So thinking about the radiated cable, let's say you got your master radio and you're connected to the long cable, and along that cable you got several mobile clients, and they're moving along up and down, back and forth, communicating to a master. But what if the production line is not linear, or what if it's very long? So this slide shows a radiated cable that also has an extended segment. So as a mobile carrier moves along the production line, it'll eventually get to a point where it needs to roam or switch. And it'll actually roam or switch from one cable segment to the next. So as I mentioned before, Prosoft has very fast roaming and switch times. So this presentation so far is mainly, as I said earlier, would be just a discussion of general concepts for industrial wireless. But before closing out, I just want to take a couple minutes to show a Prosoft utility that helps you design a system. It'll also help you generate, bill of materials. So the next few slides, I'll be using the Prosoft Wireless Designer software. In more particular, I'll be selecting the use of an RLX2 product. All of the Prosoft RLX2 products are compliant with IEEE 802.11n. They operate in the 2.4 and the 5 gig gigahertz bands. They all have the fast roaming time that I spoke of, which is very critical to your mobile applications. They all have the same internal web page for easy configuration. They all can be configured as a master, as an access point, as a repeater, as a client, all within the same unit without having to order different multiple part numbers. They also have, IP67 and hazard location packages for hazard locations. So the Prosoft Wireless Designer software, again, helps you specify radios, cables, antennas, or any other accessories you might need. So right now I'm just going to switch here from this presentation and go off to the software and design together a simple system. Okay, so the first thing I'm going to do is just design a new network. I'm just going to give it a name. I'm going to call it point. It's going to ask me whether I want it to be indoors or outdoors. I'm just going to say outdoors. At this point, it gives me the option to go through here and just, to select what radio I want to use. I'm just going to choose a radio that's more popular that I've used in the past, the RLX2 IHNF. It'll give us a brief description of some of the specifications of the radio. I'll click next. And then it's going to ask me what country I'll be installing this in. And once it starts up, it gives you a base radio. It picks out some miscellaneous antennas and cables that you can either use or change later. So at this point, I'm kind of finished with all the preliminary. And the first thing that's going to pop up is going to ask me to define some things about our initial site. So I'm going to call this West End. And it's going to ask me what's the distance between the radio and the antenna. I'm just going to put 50 foot. Okay. When I do that, it puts an antenna site up. I'm gonna right click and say pick, and we'll grab that site and move it over, get it out of the way a little bit. I'm gonna right click again and go back to my site tool. So I've got my site tool up. If I click somewhere on the screen, same thing pops up. It's gonna ask me for some basic information about the site. I'll call this East End. And again, I'll give that a distance from the radio to the antenna of say 50 feet. And we'll go back and right click and click pick so I can move that around. So I got two radio sites I'm going to want to communicate to. I can have more. The next thing I'm going to do is I'm going to right click and say link. At this point, I'm going to select this site, connect it to that site, and say basically I want to communicate between these two radios. Then it's going to ask me what's the distance. Well, if you know the distance, type it in. There's also a way you can type in GPS coordinates. We can do that over here a little bit later. So I'm just going to put a mile. Let's say they're a mile apart. So I'm going to grab it, move it over, kind of line it up. And the first thing that happens when you tell it how far away we are is that it takes the radio type that you selected, the distance of the antenna cable, whatever type of antenna that the software previously originally spec'd out, and then based on that distance, it's going to say, hey, you can have an expected RSSI of negative 68 dBm. So if you remember earlier, we talked about the RSSI, which is the received signal strength indicator, and that Prosoft suggested designing a system on paper that had something of around negative 65 dBm or less. And here's what we got. We got a 68. So and it's got a green line here. So if we double click it, it says the 68 is actually good. It's not excellent, but it's good. So what I'm going to do is I'm going to go back and say, okay, what can we change? Simple things can we change to kind of get that down. So I'm going to double click over here on the West End site. And as you can see, I've got my antenna, got my radio, got an antenna cable between the two. I can click on the antenna and I can pick different antennas if I wanted to. But we're very close to being where we want to be in terms of the RSSI. So I want to go down here to cable and I want to click it. And it shows that I'm actually using an LMR 400 type of cable. And the overall cable dB loss is 5.9 or roughly 6 dB. So if we remember that, 6 dB, I want to go down and pick an LMR 600 and it dropped to 4 or a little over 4. So we just improved our RSSI of almost 2 dB. So I'm going to accept that and click OK to close that window. And it indeed dropped from 68 down to 66. So I'm going to do the same thing over here to this other site. I'm going to take that antenna cable and drop it to a LMR 600, which is a better cable with lesser loss. Click OK, click OK. And now we have our RSSI of negative 65 dBm. So at this point, we really have 2 radio systems. If all we're going to do is communicate point to point, and we're pretty much done. And one thing this software doesn't do is it doesn't take into account obstructions. It assumes line of sight and all those other things that you have to provide that information on your own. But one of the good things it does do is the software allows you to go up and click this little tab up here that's called Site Details. And we can see that item number 1 here is our radio. There's a part number. Item number 2 is a small couple-foot pigtail connector that goes to item 3, which is a lightning protector. That's a bulkhead mounting connector that allows you to pass your antenna cable from internal of an enclosure to the external. Then item 4 is your long antenna cable, going to item 5, which is your antenna. And you can look at this type of detail for both site 1, the west end, and site 2, the east end. You can also click this tab and get a full parts list. So I just set up 2 sites that are pretty much duplicates, so I got 2 of everything. Prosoft does throw in a weatherproof kit that does include some vulcanizing tape, so when you're putting all this stuff together, especially your connections up to the antenna or anything that's external, it's exposed to weather, you want to use the vulcanizing tape to keep the moisture out. Another thing this software does is I can click File and Export, so I can take the parts list I just created, export it to a CVS file that can then be opened up in Excel and added to my overall parts list of my application. So that's a quick overview of the Prosoft software. And that pretty much ends our presentation. I'll pass it back to Rachel to see if there's any questions in the chat window. Otherwise, I want to thank everybody for taking the time out to be with us today.
Great, thank you, Jeff. That was great. We don't have any live questions in the chat at this time, but we'd like to go ahead and give a couple minutes in case folks have some questions now. While we wait, I want to remind you that you can always reach out at the email address that's there on the screen, macandmaclive@macandmac.com. You can send us your questions even after this live stream is ended if you're watching it as a recording, and we'll pass them along to Jeff. Just let us know the name of this session when you do send those emails so we know who to send it to. And all right, I want to thank everyone for joining us here today. Thank you, Jeff, for this great presentation, and thank you, Victor, for being our resource out in the comments section. We hope this session was informative and engaging for everyone. Remember to subscribe to the McNaughton-McKay YouTube channel for more industry content, and we look forward to seeing you live again soon. Thank you, everyone. Have a wonderful day.